In this video, we're going to look at the topic of big data. Big data can't be processed by traditional means. So when we talk about big data, it's a generic term for large or complex data sets that are difficult to store and difficult to analyse. Really, it's too big to fit on a single server. It could be too diverse in character. It could be structured, semi-structured. The production of data could occur at very high rates. So, and there's an example there. Every second on Twitter, 6,000 tweets are sent. And this could lead to concurrency issues. Additional servers are used to patch problems initially, or distributed database systems. When we talk about data, we talk about data being collected for a specific purpose. Often, data is given a structure, and we have the knowledge of that structure, the knowledge of the data, and we can use that data in a way that is structured. For example, it fits well into attributes in a database table. If the quantity of data can't be structured and it can't be analysed, then sometimes it can be difficult to produce any useful results, and that's the challenge that we have when working with big data. If it can't be turned into useful information, there's little point in collecting it in the first place. So data is unprocessed information, and information is meaningful data. So the data, can we give it structure? Then it becomes information, and if we can use that information, it becomes knowledge. Examples of big data fall into many categories. For example, we have scientific research, often collecting data from weather sensors, collecting it from telescopic observations, biological research, and this comes in huge volumes, often measures in petabytes or exabytes. If we look at retail and look at the use of online retailers, we could have millions of customers generating billions of sales, and this is big data. The banking sector now, think of the amount of transactions that are placed every single day, week, year. We have up to billions a year. The government, NHS records, appointments, operations, mobile networks. So with an estimated 4.6 billion mobile phone contracts around the world, then we think of customers, call data, the logs of all of the texts. And we can use many real-time applications. Think of share prices, the stock exchange. So these are examples of big data, and obviously the internet, social media, social attitudes, trends. We can talk about big data fitting into three categories. Talk about volume, velocity, and variety. So volume, the data is too big to fit on a single server. Velocity, the data changes quickly, and it may include constantly changing data sources, streaming data. This could be milliseconds to seconds to respond. And variety, kind of data variety now. We've got structured, unstructured, there's text, multimedia, all kinds of variety of data. Big data tends to be measured in terabytes, petabytes, heading towards exabytes and beyond. So in 2015, Facebook generated 10 terabytes of data every single day. So that's a huge mass of data. If we consider the 3 V's of big data, we can see a variety heading out to the right hand side: text, CSV, video, XML, SMS. We can see our volumes: kilobytes, megabytes, gigabytes, terabytes, exabytes, petabytes, zettabytes, yottabytes, and that's heading out. And we've got the velocity. Are we having it in real time or closer in? Are we having it in batch? So we said the volume, in terms of the volume, the size of the data to be processed. We must analyse the data as a single data set. Physical data centres that deal with zettabytes of data may not necessarily be big data. We could sometimes have big data sets or big data centers that have this data, vast amounts of data, but it's not necessarily big data. That data may be used by organizations. It may be structured in, for example, like Amazon, products table or records, and it may have a structure in there. It becomes big data when the data volumes that need to be processed outgrow the storage and processing capabilities. So it's when alternative data processing is needed, when it's distributed across more than one server, when we've got big blocks of data of 64 to 128 megabytes. If we think of traditional blocks of data would be 512 bytes. Blocks of individual files, they could be spread across more than one server, and several servers can be connected by a single switch, or you may even have multiple switches. We talk about fault tolerance. This enables a system to continue to operate properly even in the event of a fault, and so we're looking for more fault tolerant systems. And then we talk about the distributed file systems that rely on the commodity hardware. So commodity hardware, inexpensive magnetic hard disk drives, and these need to become fault tolerant. In terms of distributed processing, we talk about that as being the principle of spreading large and complex tasks over a number of computing servers. Typically one computer would be allocated as the master computer, and in the network that will control the others through the operating system and specialist software. And each computer on the network will be allocated its own subtask, and messages are then passed between the computers in order to meet the overall goal. This could be implemented on a client server or even a peer-to-peer basis. And this could be implemented as a distributed network with each of the main computers being a server and then further workstations being attached to the server. Big data is almost always needs to be distributed computing of some sort. Sometimes we might have a distributed program, and this is written specifically to be used in a distributed processing environment, or we might have a functional programming techniques used in there, which we'll get onto in a moment. Here's just a couple of links that you could watch to find out about Facebook Data Center. Really worth watching and see how some of the big data is dealt with. Second aspect of big data approach is parallelizing the execution of programs. This is done with the function to data model, and in this function to data model, because there is so much data, the analysis program is sent to the data. So what actually happens is that we get a copy of that program that's sent to every server, and that uses something called the Hadoop, which is an open source, highly scalable, distributed batch processing system for large data sets. And at the heart of this borrows a technique from functional programming, and you remember we looked at the technique MapReduce. So MapReduce is a programming model which uses a parallel distributed algorithm to process large data sets at rest in a cluster, and it will take the input and it would split it into smaller parts and execute the code of the mapper onto every part of that. So we did look at MapReduce when we looked at functional programming, and here is then the tie-in between functional programming and big data. Because functional programs differ that they use expressions as similar to normal mathematical expressions in order to evaluate that data. And we'll have a look at that shortly. So issues with big data is that data sets are so large they're difficult to store, difficult to analyse. Unstructured data can be very difficult to analyse. Specialised software needed to manage and then extract meaningful information. So if we have a think of how this data comes in, how do we actually find something meaningful in it, especially if it's unstructured? And data, if it's constantly changing, then how do we find patterns? There could be an issue with concurrency, which is where several users are working on the same data at the same time. Most big data sets are stored in data warehouses, and we use fact-based modelling attempts to identify fundamental facts within the data, and this in turn identifies all of the entities in the data, and we look at using diagrams or natural language. So we've already mentioned about distributed processing, the idea of splitting work over several computers, and about one computer being allocated a master computer, can be implemented peer-to-peer or client-server. In terms of the functional programming, if we think imperative is where it's written in programmer-defined sequence, variables are mutable, which means they can be changed, program will have a state and can therefore have side effects. So the changed state of a variable can have the impact of the program. We might change the contents of that variable, its state actually changes, and that can have knock-on effects. If you have a look, if we've got local, global variables, and different procedures and functions could alter the way that a variable works. In terms of functional, functions are used to create programs. We don't use variables in functional programming. We use expressions like in maths. We have no states, and therefore that makes to have less side effects, and this makes it more useful in terms of big data. Key points are that big data is data that's either too large or too complex to be handled using traditional means. Big data is becoming more common, particularly with the volumes of data being generated via the internet. Some data cannot be structured into columns or rows like a traditional database, so therefore we have big data. Unstructured data are more difficult to query, and techniques such as machine learning are used to interrogate unstructured data. Machine learning is where it looks for patterns in data. So when quantitative data is stored in standard relational database, it's easy to ask for a query. In terms of machine learning, we look for pattern recognition, we use artificial intelligence to look for keywords, key text, to find out what is happening within that data. Data models can be produced to try and understand how big data is structured. And big data is often spread across a number of servers in order to cope with its size. And where this is the case, there is an added complication of working on data split across two or more servers. But overall, that is the introduction into big data.